Metro Line 1's progress in installing over 70 bridge beams marks a major milestone in its construction, akin to the achievements seen in projects like the Link Light Rail's Angle Lake Station in Washington. Much like Angle Lake's pivotal role as a transit hub, Metro Line 1 aims to serve as a crucial transport link, promising smoother connectivity and reduced traffic congestion. Metro Line 1, similar to Seattle's One Line, is a comprehensive project designed to improve urban mobility. The installation of bridge beams is critical to the line's elevated sections, which will allow it to bypass ground-level obstacles and ensure uninterrupted service. This structural phase is comparable to the elevated guideway built for Angle Lake Station, which spans 1.6 miles. Elevated tracks, supported by these beams, offer a long-term solution to the issues posed by densely populated or complex urban layouts. Metro Line 1 has faced delays and funding challenges, similar to those encountered during the construction of Angle Lake Station. Angle Lake's project initially faced setbacks, with its completion delayed beyond the original 2006 target. Funding issues meant it was only after the approval of a 2008 ballot measure and a subsequent increase in federal grants that the project could be completed ahead of the revised schedule in 2016. Metro Line 1's project timeline and funding strategies reflect similar complexities, emphasizing the importance of community and governmental support to achieve timely completion. The installation of bridge beams represents a physical and symbolic advancement for Metro Line 1. Like Angle Lake, which connects various districts and vital locations in Seattle, Metro Line 1 aims to link significant areas in the city, enhancing access to business hubs, residential neighborhoods, and other key destinations. The A40 Rhine Bridge Duisburg-Neuenkamp, set to become a major landmark for Duisburg, is one of the most ambitious infrastructure projects in the region and Germany's largest cable-stayed bridge. This modern two-pylon bridge, built to replace an older structure, features two parallel bridge sections, each dedicated to one direction of travel. With a record-breaking central span of 380 meters, this bridge represents a milestone in German engineering. This new structure is impressive not only for its size, but also for its strategic design. Standing 75 meters high, the pylons are integral to the bridge's two superstructures, which extend over 800 meters in length and 68 meters in width. To meet modern standards, the bridge integrates steel-concrete composite constructions in the approach areas and fully steel constructions across the river spans. This mix of materials allows for a durable and stable structure capable of supporting high traffic loads over the Rhine. Additionally, pedestrian and bicycle pathways are built alongside the roadway, ensuring safe and convenient travel for non-motorized commuters. The construction of the bridge utilizes advanced engineering techniques that highlight the project's complexity and innovation. The approach sections are built with the incremental launching method, a process that involves gradually moving pre-constructed sections into position. For the main spans over the river, the free cantilever method is applied, which allows the bridge to extend outward in sections without the need for temporary support structures over the water. A distinctive feature of the project is the planned transverse shift of the southern bridge span by 14.4 meters, an engineering feat previously unseen in bridge construction. Designed to handle both current and future transportation demands, the A40 Rhine Bridge emphasizes safety and environmental standards, meeting rigorous modern regulations. This forward-thinking approach aims to reduce maintenance needs and extend the bridge's lifespan, making it a sustainable infrastructure investment for Duisburg and surrounding areas. The Rhine Bridge Hard-Fussach, spanning 255 meters across the Alpine Rhine between Hard and Fussach, is undergoing essential updates to accommodate increased flow capacity and modern traffic standards. This project, part of a broader effort to improve flood protection for the Alpine Rhine section, from Reichenau in Switzerland's Graubünden canton to Lake Constance, addresses the heightened flood risk associated with potential peak flow rates. Previously capable of managing 3,100 cubic meters per second, the flow capacity is being increased to 4,300 cubic meters per second to mitigate damage risks from extreme flood events. The existing bridge structure no longer aligns with modern traffic engineering standards, necessitating a significant overhaul. Work on the bridge's substructure, which began in September 2020, involved a phased construction schedule adapted to the seasonal flow variations of the Rhine, with critical work undertaken during the winter months, when river discharge is typically lower. This phase concentrated on building new abutments, piers, and auxiliary piers along the Rhine, aligning with the strategy to incrementally launch the steel superstructure from Fussach towards Hard. The construction of the substructure was sequenced to maximize efficiency and safety under challenging conditions, including poor subsoil and unpredictable weather. The process began with securing the excavation pits on the Fussach side, where sheet piles were driven deep into the ground to stabilize the earth for further construction. This initial stabilization was achieved using heavy-duty machinery equipped with special guide systems designed to embed individual steel profiles or sheet piles securely into the ground. Following this stabilization, the pier structures were built upon ductile small driven piles that served to transfer the load of the bridge securely into the ground. Each pile installation involved a hydraulic excavator and impact hammer to drive the piles into position. To enhance load-bearing capacity, a driving shoe was installed at the base of the first pipe, enabling cement slurry to be pumped around the pile casing, which bound the pile to the surrounding soil for added strength. Reinforcing bars were also installed in the piles to counteract tensile stress. Despite the rigorous planning, the subsoil posed significant obstacles. The foundation consisted of soft, unstable lake clay deposits, which proved challenging for securing the bridge supports. However, by the end of November 2020, the Fussach side abutment was completed, and by early December, Auxiliary Pier Pennsylvania 3 on the upstream side was erected, marking a key milestone that paved the way for the launch of the bridge's superstructure. The team faced formidable demands due to the sheer volume of materials and the precise timing required to keep the project on schedule. During the winter of 2020-2021, construction activities reached full intensity, with 20,000 cubic meters of soil excavated, 10,000 square meters of sheet piles installed, and 30 kilometers of driven piles embedded into the ground. Reinforcement was another substantial undertaking, as 400 tons of steel were integrated into the structure, along with 6,000 cubic meters of concrete poured for the various bridge components. Formwork prefabricated offsite facilitated a faster and more controlled assembly of the bridge piers. This approach allowed the first pier to be poured as early as November 2020. Additional shoring structures were also added in the Rhine's main channel, where working in the river's strong currents and fluctuating water levels introduced further complexity to the project. Rhine Bridge Hard-Fussach Part 2. The steel construction, the Rhine Bridge Hard-Fussach, represents a monumental feat in engineering and design, part of an essential infrastructure project that spans the Rhine River between Austria and Switzerland. This bridge, critical for regional transportation, entered an intricate and challenging phase with the initiation of its steel construction. This stage, characterized by extensive planning, meticulous execution, and innovative techniques, marks a crucial milestone in the bridge's development. The construction process, involving multiple countries and highly specialized engineering methods, showcases modern construction technology and precision. The steel construction phase began with preparatory work on a pre-assembly site near Fussach. This groundwork, completed by October 2020, allowed for the installation of auxiliary supports essential for the subsequent phases of the bridge's steel structure assembly. By early November 2020, the initial prefabricated steel components arrived at the construction site, having been produced in manufacturing facilities across the Czech Republic, Hungary, and Austria. The decision to fabricate the steel components in large sections optimizes transportation and assembly efficiency, minimizing the need for special transport logistics. With components weighing up to 90 tons, this strategy significantly reduces the complexity and frequency of transport while maintaining the structural integrity of the steel sections upon arrival. The bridge's structure is a steel-concrete composite, integrating steel and reinforced concrete for durability and load-bearing efficiency. The primary steel framework consists of two trapezoidal steel box girders that form the foundation for the reinforced concrete carriageway slab, which will be added at a later stage. This composite design not only enhances the bridge's load-bearing capabilities, but also contributes to its longevity and resistance to environmental stresses. The steel sections were assembled on the western bank of the Rhine, where individual components were welded to form a cohesive structure. This welding process is crucial to the bridge's stability and load-bearing capability. Manual gas-shielded welding is employed for most of the assembly, while submerged arc welding is utilized for creating the longitudinal seams on the bridge's top face, providing greater precision and strength. The quality and durability of the bridge's welded seams are paramount, as these connections must withstand the dynamic loads imposed by heavy traffic and environmental forces. Special preparations are made to ensure the seamless transition of welded joints, including post-treatment processes such as grinding and sandblasting, followed by the application of multiple coating layers. These coatings protect the steel against corrosion and environmental wear, extending the structure's lifespan. To protect the welding and coating activities from weather elements, a temporary workshop was erected on site. This facility ensures that the welding and coating processes are conducted in controlled conditions, preventing delays and maintaining the high-quality standards required for the bridge's components. An innovative approach to bridge construction, the steel structure of the Rhine Bridge is constructed using the incremental launching method, a complex engineering approach where sections of the bridge are built sequentially and pushed forward incrementally. This method, ideal for crossing challenging spans like the Rhine, allows construction to occur on one bank while progressively advancing the structure across the river. Each section is fabricated in a production facility behind the abutment, then aligned and integrated with previous sections to form a coherent bridge span. This cycle continues until the bridge reaches the opposite bank. Between February and October 2021, 10 attachment phases and 10 shifting phases were completed, each with varying shifting lengths. 4 hydraulic presses, applying a combined thrust force of 240 tons, were utilized to push each section forward in precise increments. Due to the structural demands of spanning the Rhine, auxiliary bracing was necessary to stabilize the bridge as it was incrementally advanced. In April 2021, a complex bracing setup was installed, consisting of 2 steel towers, each standing 21.5 meters tall and weighing 18 tons. These towers, fully assembled on the ground and lifted by crane, were bolted to the supporting structure to provide stability during the incremental launching process. A series of 15-strand rope bundles were then attached to the towers and pre-tensioned to 120 tons to further stabilize the bridge structure. These cables mitigate deformation during the tensioning process, which is carefully monitored and recorded by structural engineers to ensure that the bridge can withstand future dynamic loads. Given the bridge's crucial role in regional infrastructure and the significant forces it will endure, rigorous quality checks are applied throughout the steel construction process. The welds are meticulously inspected to ensure they meet stringent durability and strength standards. Ultrasound technology is employed to detect even the smallest flaws, as any defect in a weld could compromise the bridge's integrity and safety. Additionally, the coatings used on the steel components must meet high-quality guidelines, and only approved materials are permitted for use in this phase. The steel structure's advancement across the Rhine presented numerous challenges. During incremental launching, structural stresses fluctuate as new sections are pushed forward, influenced by temperature changes from sunlight, wind conditions, and potential ground shifts beneath the piers. Continuous monitoring of these variables is crucial to ensuring the stability and alignment of the advancing bridge structure. Each bridge construction project is unique, making large-scale prototypes impractical. The unpredictable environmental conditions and specific ground characteristics demand real-time problem-solving and adjustments, requiring a high level of expertise from specialized construction teams. Rhine Bridge Hard-Fussach Part 3. The superstructure, the construction of the Rhine Bridge Hard-Fussach, reached a significant milestone in early October 2021 with the completion of the longitudinal shifting of steel box girders into their final position. This achievement marked the beginning of the next phase, completing the bridge's superstructure. The bridge, which spans 255.6 meters with a width of 24.37 meters, represents an impressive feat of engineering. It combines a four-span steel composite design with a dissolved cable structure, supported by new piers and pylons designed for both structural support and aesthetic appeal. Assembly hall removal and temporary support dismantling with the steel box girders now shifted into position. The temporary assembly hall, which had served as a controlled environment for pre-assembling components, was dismantled. Additionally, auxiliary spans used during the initial phases of construction were removed using mobile cranes. At this stage, precise adjustments to the steel structure's positioning and height were made. These fine adjustments were necessary to ensure proper alignment and load distribution once the bridge was operational. Spherical bearings were installed at key points to manage the load transfer between the superstructure and the substructure, accommodating tilting and displacements within the bridge. These bearings consist of a spherical cap and a concave base, designed to support high forces while allowing the necessary movement. This mechanism plays a crucial role in both stability and durability, particularly in withstanding the natural shifts and rotations that bridges experience over time. With the auxiliary structures removed, the concrete carriageway slab was set to begin. Using a 100-ton composite formwork carriage measuring about 25 meters in length, construction teams assembled segments of the slab in stages. By late October, the composite formwork carriage, pre-assembled in sections weighing up to 16 tons, was lifted into place. The slab construction presented unique challenges, particularly as it extended into the winter months. Starting in December 2021, the teams contended with cold temperatures and snowfall, which slowed concrete curing times. When temperatures drop below zero, concrete can freeze, so teams employed various methods to ensure adequate curing despite adverse conditions. By following the Pilgrim step method, the construction process moved in a series of forward and backward steps, carefully controlling the tensile stresses within the concrete to prevent cracks. In this method, field areas were completed before the support areas on the piers and abutments, allowing for gradual load distribution across the bridge. In April 2022, the 12-meter-high steel pylons, visual focal points of the bridge, were transported to the site and lifted into place. Each pylon weighed approximately 60 tons and was installed with precision, using articulated bearings and 3 auxiliary struts to achieve accurate triaxial alignment. Since these pylons would ultimately rely on tension cables for stability, they were first held in place with temporary supports, with each movement closely monitored to ensure accuracy. Once the pylons were in place, the installation of the stay cables began. Each cable package consisted of high-tensile steel strands with up to 99 strands bundled per package, and a total length of 100 kilometers of cable was installed. The cables were tensioned strand by strand, following a complex sequence to apply a pre-stressing force of up to 900 tons per package. This extensive process occurred between May and July 2022. Given the bridge's proximity to the roadway, a comprehensive fire protection system was applied to the cables. This system is designed to keep the steel strands within a safe temperature range of 300 degrees Celsius for at least 30 minutes in case of a fire, thus preventing permanent damage to the cables. Following tensioning, the anchorages and the pylons and anchor blocks were grouted with epoxy resin to ensure corrosion protection. The bridge's stability is further reinforced by a fixed abutment on its western end, which serves as a rigid frame corner capable of transferring both longitudinal and uplift forces from the superstructure to the substructure. On the opposite end, an abutment allows for the bridge's longitudinal expansion, accommodating up to 36 centimeters of movement due to temperature changes and load shifts. This arrangement reduces the need for additional roadway crossings, simplifying maintenance and minimizing wear over time. To protect the deck's structural integrity, a waterproofing membrane was applied after preparing the substrate. This began with an epoxy primer, followed by the edge trim construction. Using a formwork carriage suspended from the cantilevered slab, workers constructed the edge beams in segments, totaling 28 sections by mid-August 2022. These edge beams provided additional structural support and enhanced the bridge's appearance. With the edge beams completed, the entire steel structure was cleaned, and a top coat of high solid polyurethane was applied to the steel box girders. This coating, with added micaceous iron oxide, offered both weather resistance and aesthetic appeal. It was applied through high-pressure spraying, ensuring uniform coverage and durability against environmental factors. Following the top coating, prefabricated bridge railings and guardrails were installed, with asphalt layers subsequently added. By November 2022, the bridge was ready for traffic, completing construction in just 2 years despite significant challenges. Meeting construction challenges and achieving project goals, the Rhine Bridge Hard-Fussach project faced numerous obstacles, from the complexities of its structural design to challenging subsoil conditions, proximity to the Rhine's danger zones, and supply chain disruptions caused by the COVID-19 pandemic. Success in meeting the ambitious construction timeline and achieving the high-quality standards set by the client was only possible due to the close collaboration of all involved parties. This collective effort, along with meticulous planning and adaptability, allowed the project team to overcome difficulties and complete the bridge on schedule.